Today I am going to start circles. Okay, circle, before I start circle is a closed figure which is equidistant. Circle is a path of a point, closed figure, and it is a path of a point which is equidistant from the fixed point. Okay, so this is the point and this is path of the point. So when there will be this is now when I have a line outside a circle. This is figure 1. Outside a circle, the line is not touching the circle. Line is not touching the circle. Gradually, when I proceed to it, then it will be touching the circle, and when I again proceed, then it will be cutting the circle at 2 points. Cutting the circle at 2 points. Now, the cutting the circle at 2 points, that is called secant. That is called secant. Okay. Now, when a line cuts the circle into 2 distinct points, and then the line is called a secant. Line is called, that line L is called secant, and the portion which is between the circle A and B, between the circle, the portion of the secant which is inside the circle is called chord. Chord is a part of a secant. Chord is a part of a secant. Okay. The distance between these points are on the circle, and in the figure AB is the chord. Done. Tangent to the circle. When I proceed it, then gradually if I carve this side, so it will touch just at a point P. Just at a point P. Then this line is the tangent to the, when it touches the circle at just at one point, then it is called a tangent. A tangent is tangent to a circle is the line which intersects the circle only at one point and one point. Then that is the tangent. Tangent in the figure, third figure is the tangent. Third figure is the tangent. Okay. There is only one tangent at one point. How many tangents can you draw in a circle? You can draw infinite number of circles, infinite number of tangents at different points. There are a collection of points. A circle is a collection of points which is equidistant from a fixed point. So every point there will be one tangent. Okay. And how many secants you can draw? Many. How many secants you can draw? Many. Okay. A tangent, then tangent is the special case of the secant. Here, a tangent is to a circle is a special case to the secant of the secant when the two endpoints coincide. A and B coincide here. Yes, coincide. So that means distance between the circumference and the tangent at that point is 0. No 0. It is a 0. It becomes 0. Yes. Achha. Then I go for a theorem. The tangent at the point of contact. Point of contact means where it is connecting the circle, where it is touching the circle of the contact of the circle is perpendicular to the radius at the point of contact. At the point of contact. Okay, that means my figure is here. This is a circle with center O. Circle with center O. It is touching XY is a line, and that is a tangent. and it is touching circle at P. It is touching the circle at P. Yes. Yeah. We have to prove that OP is perpendicular to the tangent XY. Perpendicular means shortest distance is always the perpendicular. Shortest distance is always the perpendicular. With the help of that, I am going to prove that theorem. Given a circle with center O and XY is a tangent at the point of P, to prove OP perpendicular to XY, to prove OP perpendicular to XY. Now let Q be any other point on the tangent. We join, this is a construction. Q be the any other point here. We join OQ, then we join OQ. Achha. Now OQ is obviously greater than OP. Why? Because P is on the circle, Q is outside the circle. Outside the circle is greater than radius. Inside the circle is less than radius. Now it is outside the circle, it is greater than the radius. So OP, Q is the another point. Here OQ is greater than OP. Yes, since OP is the radius. Similarly, for another point on XY, OP is the shortest. Shortest distance is always perpendicular. Therefore, OP is perpendicular to XY. The lengths of the tangent, theorem 2 says, lengths of the tangents drawn from an external point of a circle are equal in length. Equal in length. Okay. Given what? Given my theorem. Theorem is given. Given is given O is a circle. P is an external point. P is an external point. PQ and PR are the two tangents. Are the two tangents of circle center O, whose center is O, whose center is O, okay. To prove PQ is equal to PR. Construction. We join QO, RO and PO. Proof. In the last theorem, we have studied that radius at the point of contact is always perpendicular to the tangent at a point of contact. Yes. Proof. In triangle PQO, right triangle, it is a right triangle. In right triangle PQO and right triangle PRO. PRO. OQ is equal to OR, radii of the same circle. Radii of the same circle. Angle, radii of the same circle, and angle PQO is equal to angle PRO is equal to 90 degree. Since radius at point of contact of a tangent is perpendicular to each other, and PO is equal to PO common implies triangle PQO similar congruent to triangle PRO by RHS. Implies PQ is equal to PR CPCT. CPCT is congruent parts of congruent parts of the congruent triangle. Okay. Now again, I explain you the theorem says that when two tangents are drawn from the external point, it is equal. They are equal in length. Construction is that construction is that we join OQOR and PO. There are two triangles POQP and ORP. Then in OQ is equal to ORY. They are radii of the same circle, and angle PQO is equal to angle PRO 90 degree because radius at the point of contact is always perpendicular. PO is equal to PO common. Triangle PQO similar to triangle PRO by RHS. Okay. Implies PQ is equal to PR CPCT.